Hello everyone, my name is Swati Giridhar, Computer Science Lecturer in Shakthi PU College, Shakthi Nagar, Mangalore. Today I am going to conduct a session on logic gates from 2nd PUC Computer Science textbook. So, Chapter 3 Logic Gates. Let's see what are the objectives of this chapter. So, we are going to learn different types of logic gates and how can you design a logic circuits using the gates. So, let's see the definition. What do you mean by logic gate? A gate is an electronic circuit which operates on one or more input signals and always produce an output signal. Here you should make a note on one or more input signal. It can take two or more input signals or one or more input signals, but always produce an output signal. This can be a gate with one or two input signals and produce an output signal. And here you can see two states, that is on state and off state. On state is always noted with 1 and off state is 0. And we can also tell this one as high, state high, and this one as low. So in logic gates we just have two states, that is on and off. So what are the different gates we are going to learn? Let's see different types of gates in this chapter. So different types of gates are NOT gate, AND gate, OR gate, and we have NOR, NAND, XOR and XNOR. These are the different types of gate we are going to learn from this chapter. From this chapter, so these three gates are called as basic gates and all the other gates are called as derived gates. So what do you mean by basic gates and derived gates? Basic gates are gates from which we are going to perform three basic operations. That is NOT operation, AND operation and OR operation. NOT operation is always a complement and we denote it using a bar, and NAND operation with a dot operation, we call it as a dot operation, and OR with plus operation. We are going to perform plus operation. So how can you explain derived gates? These gates are derived from basic gates. So gates which are derived from basic gates are called as derived gates. So let's see all the gates one by one. So first one is a NOT gate. It is also called as inverter gate. So let's see the definition. An inverter gate is a gate with only one input signal and one output signal. So it only has one input signal and always produce one output signal. The output is always the complement of or opposite of the input signal. So every gate has its own symbol and its own input and output states. So let's see how can you design or what is the symbol for NOT gate. So this is a symbol used for NOT gate, or it is also called as inverter gate. Why it is called as inverter gate? Because always the output is opposite of or a complement of input. So if 0 is an input given to this gate, so you can expect 1 as an output, because 0 and 1, always we just have only two states, that is 0 and 1, high or low or high and low. So that is, this is a symbol used, and if it is 0, the output you expect is 1. So if you give 1 as an input to this gate, you can get 0 as an output. And let's design a truth table for this. So with two states we have X, the output is X bar. So generally you can write, if you give X as an input, the output produced is always X bar, which is complement of input state. So we are going to write the all possible values. What do you mean by truth table? This is also called as truth table. So what do you mean by truth table? Truth table is a table which contains all the input states and output states, all possible input state which gives you the output state. So here we have only one input, so the possible input is 0 and 1. So the output what you can write? So always if you have a 0 as an input, the complement of 0 is 1, and if you have 1 as an input, the complement is 0. So the truth table for NOT gate can be written as 0 and 1 as the input symbols, and output will be 1 and 0. So the next gate is OR gate. OR gate has two or more input signals and always produce one output signal. So output signal is high if any of the input signal is high. What do you mean by that? OR gate takes 2 or more input signals and produce only one output signal. So here students, you have to note 2 or more input signals. Inverter gate takes only one input signal and one output signal, but all the other gates takes 2 or more input signals and produces one output signal. So you cannot design a OR gate or next all the other gates with one input signal. You should have more than two or more than 2 input signals, and it always produces one output signal. And the output signal is high if any of the input signal is high. So let's see, while drawing the truth table, we can see what do you mean by that. So what is the symbol for OR gate? So OR gate symbol can be written as, what do you mean by this? This is a input state. To input signals, you can generally written as X and Y, and the symbol is, this is a symbol used for OR gate, and the output, the operation used is this is called as logical addition for OR gate. So you can write the output yes. F is the output, that it is equal to X plus Y. This is a logical addition of 2 input signal. So you have 2 or more input signal. So you can design a logic gate with 3 input signal. This can be written as, this is a 3 input OR gate which takes inputs X, Y and Z, and output F can be written as X plus Y plus Z. So OR gate can take more than 2 input signals and always produce a single output signal. So if you have a 2 input, so possible states you have 2 to the power 2, that is 4 possible combinations of input. So if it takes 3 input signals, 2 to the power 3, that is equal to 8 possible input combinations. So if you have possible input combinations, let's see how the output will be. That is called as designing the truth table. So 2 input truth table will be like this: X, Y, F is equal to X plus Y. This is how we can write the truth table. So what are the 2 input OR gate has 4 possible combinations. Let's see what are the possible combinations. You can give low input for X, low input for Y, or you can give low input for X and high input for Y, or you can give high input for X and low input for Y, or you can take 1 and 1, means both the input signal has high input. So these are the only possible 4 combinations from 2 input OR gate. Let's see what will be the output. So here you need, if any of the input signal is high, the output signal is high. That means this is high, this is high, this is high. Only 0. OR gate produces 0 only if 2 input or all possible inputs are low. For other values you have high. This is a truth table for OR gate. The next gate we have is a AND gate. Similar to OR gate, we have AND gate takes 2 or more input signals and produces one output signal. When all the inputs are high, the output is high. Otherwise, the output is low. This is a definition for AND gate. You can expect this one for 1 mark question. So what do you mean by AND gate? AND performs logical multiplication. This is an operation for AND gate. The symbol used for AND gate is for 2 input AND gate. This is a symbol used, and 2 input generally represented as X and Y, and the expression is written as X dot Y. So 2 input AND gates have 2 or more inputs and 1 output. So how can you design 3 input AND gate? These are the input signals and this is a gate, and you have a output signal. This can be generally represented as X, Y, Z. F is equal to X dot Y dot Z. So you, after writing the symbol, you have to write the truth table. What do you mean by truth table once again? It is a all possible combinations, input combinations and output combinations. So output combinations, we just have only one output signal, but input combinations is different. So with the 2 input, you can write X, Y, F. F is equal to X dot Y. So what are the possible combinations of input? 0, 0, 0, 1, 1, 0, 1, 1. Only 4 possible combinations because 2 to the power 2, that is equal to 4. So how can you write this? You can see the next point here. When all the inputs are high, the output is high. Means if 2 inputs are high, the output is high. For all other combinations, you have 0. It's like a simple multiplication. 0.0, 0.1, 1.0, 1.1. Only 1.1 produces high output. For all other combinations, we have 0. So let's see how the 3 input OR gate looks. So we have X, Y, Z. I'm going to just write F here. So what are the input combinations? We have 2 to the power 3 is equal to 8 input combination. This can be simply written as 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. You can see here 1, 2, 3, 4, 5, 6, 7, 8 combinations or possible input values. So how to write output? You don't have to worry much about it. Only output signal is high when all the input signals are high. So you can get high only for last option. For any one output signal is or input signal is 0, the output is 0. As simple as that. You can write 0 for all other combination and only high when all the input signals are high. So we have NOT gate, AND gate and OR gate as a basic gates. Now we have derived gates. Under derived gates, the first one is NOR gate. This gate can also be written as NOT OR gate. That means complement of OR gate. So how can you write the definition? The NOR gate has 2 or more input signals but only 1 output signals. Other than NOT gate, all the other gate has 2 or more input signals and always produce 1 output signal. So if all the inputs are low, then the output is high, because since it is a NOT OR gate, it is a complement of OR gate. So output signals, you can see here 0, 0 produces 1 and all other combination produces 0. In X plus Y, that is OR gate, we have 0 here and all the other values has 1. Since it is a complement is written as X bar. You can see X plus Y is a OR operation and it's a complement. Since it is a NOT OR, NOR is nothing but NOT OR, it can be written as X plus Y whole bar, which produces output if all the input signals are low. All the other combinations will produce 0 output. For input signals are low, the output is 1. So how can you write a symbol for this? Symbol can be simply written as OR. This is a OR and you are going to write a NOT operation. So X, Y, here you are going to get X plus Y and you are giving this one input as one output as input to the NOT gate that produces X plus Y bar. So this can be written as, this is a symbol for NOR gate. X, Y will give you X plus Y whole bar. This is a symbol for NOR gate and this is a truth table for NOR gate. So AND gate has 2 or more input signals and produces 1 output signal. If all the inputs are high, then the output produced is low. Since it is a complement of AND gate, that is NAND is a complement of AND gate, if all the inputs are high, then the output produced is low. Here you can see the truth table. X is equal to 0, Y is equal to 0 produces 1, X is equal to 1, 0, 1 produces 1, 1 and only one combination. If all the inputs are high, the output is 0. For all other combinations, you have output is high. If all the inputs are high, the output is 0. Since it is a NOT AND gate. So NOT AND gate is also called as NAND gate. So how can you write the symbol? Symbol can be simply written as AND gate, NOT, that is X, Y will give you X dot Y and NOT will complement it. So the output for, this is a symbol used for NAND gate and the output produced is, so this is a symbol. So you have to write a definition and symbol with truth table for 3 marks. You can expect 3 mark question plus 1 mark question from this chapter. 4 marks for logic gates. So the next gate we have is a XOR gate. It is also called as exclusive OR gate. So like other gates, it accepts 2 or more input signals and produces 1 output signals. And we have to check number of ones in input signals. So if you have even number of ones, the output is 0. and if you have odd number of ones, the output is 1. So you have to check the number of ones in here. Here you don't have any number of ones in an input signal, so we consider it as even. And here you have odd, because you have these are the input signals x and y, and this is the output signal. So you have odd number of 1 here and you have odd number of 1 here. So odd, I am going to just write the number of input signals, either it is even or odd number of ones. So here you have even. Accordingly the output, if you have a number of ones or 0 ones, we have output 0. And if you have odd number of ones, output is 1. Odd number of 1, the output is 1. Even number of ones, the output is 0. So you have to take care or take a note of even and odd number of ones in the input signals. And the symbol for exclusive OR gate is with 2 input signals you have input, and this is a gate, and the symbol used for operation is plus with a circle. This is the symbol for exclusive OR gate. So the next gate we have is a XOR gate. It is also called as exclusive OR gate. Like other gate, it takes 2 or more input signals and produces 1 output signal. Here you can see even numbers and even and odd. If you have odd number of ones in input signals, the output produced is 0. And if you have even number of ones, the output produced is 1 in this gate. And the symbol we use for XNOR gate is so the operation performed is dot operation with a circle. So here we have x, y as an input and x dot circle y as an output signal. This is a 2 input XNOR gate. So next we have universal gate. The universal gate is a gate using which all the basic gates can be performed. So NAND gate and NOR gate are called as universal gate. What do you mean by universal gate? Using NAND gate and NOR gate, we can produce the basic gates. What are the basic gates? We can produce AND gate, OR gate, and NOT gate, just using either NOT gate, just using either NAND gate or NOR gate. So now we have to design basic gates using just NAND gate only. So how can you design NOT gate? So if you give 1 input, NOT gate takes 1 input signal and produces 1 output signal. So if you give 1 input to NAND gate, this is just we are going to connect these 2 signals, because NAND gate takes 2 or more input signals, but we have to design NOT gate which takes only 1 input signals. So we are going to connect these 2 inputs and giving x as an input to NAND gate which produces x bar, that is NOT operation, or we are designing NOT gate. Then if you use twice the NAND gate, you will get AND operation. So here you can see 2 input NAND gate which gives you output x dot y whole bar. If you give this output as an input to this output as only 1 input to 1 more NAND gate, you can see x dot y whole bar. That you mean by bar, double bar, that performs this operation. This can be designed using De Morgan's theorem. And you have OR gate. So how can you get OR gate? You have to use NAND gate 3 times. If you want to perform OR operation using NAND gate, you have to use NAND gate 3 times. That is like x, once for x you will get x bar, once for y you are going to get y bar. Here you are going to give x bar and y bar to 1 more NAND gate which gives you x bar dot y bar whole bar. That can be written as x double bar plus y double bar. You can negate these double bars, you will get x plus y. So simply if you want to remember, you can use once NAND gate once to get NOT gate, NAND gate twice to get AND gate, NAND gate thrice to get OR gate. So next, let's see how can you design basic gate using NOR gate. So similar like NAND gate, you are going to use this gate once to get NOT gate. That is one single you are going to connect these 2 input signals and give 1 input signal to NOR gate, you will get x bar. So it is easy to get OR gate from NOR gate because it is a complement. So you have to use twice. So if you give x, y once to NOR gate, you will get x plus y whole bar, and if you give this one as an input, one more input to the NOR gate, you will get x plus y whole double bar, that is equal to x plus y. That is not just NOR gate producing OR operation, not OR. So you are negating the answer again. So if you use NOR gate thrice, you can get AND gate. That is, using NOR gate just for x once, you will get x bar. Using NOR gate just for y once, that will get y bar. If you give x bar, y bar to NOR gate again, you will get x bar plus y bar whole bar, that can be written as x double bar dot y double bar, that is equal to x dot y. So if you want to remember, simply you can see, you can use NOR gate once to get NOT gate, twice to get OR gate, thrice to get AND gate. The last part, how can you design a circuit diagram? Circuit diagram can be defined or circuit diagram can be designed just using basic gates or using NAND and NOR gate also. So here the first example, you just have to, here you can see this is a OR operation, this is a AND operation, and you have 3 inputs. This expression has 3 input. How can you design gate? Here for this you can use OR and this is AND. So you can start with X, and here for Y we have Y, Z. So 3 inputs we have, and Z you can see here, Z is a Z bar. So you need a NOT gate here to get Z bar. And here you can see AND operation. So you have to use AND gate. So the output produced will be Y, Z bar, that is Y, Z bar. So what we have? X plus Y, Z bar. So X we have here, we need a OR gate. So here you can take a input, and this one will give you, that is X plus Y, Z bar. As simple as that. You are going to check the number of inputs first, and if there is any complement form or something, and this is a gate designed using basic gates. So for second gates, let's use basic gates and derived gates. So here you can see you have 3 inputs, X, Y, Z, X, Y and Z, and this operation, this is a AND operation, and here you can see this is a NOR operation. So instead of using AND OR gate and complementing it, you can directly use derived gate, that is NOR gate. So how can you do this? You have a NOR gate here which will give you Y plus Z whole bar, and you need a AND operation. So the output produced is X. So like this you can design circuit diagrams for any expressions. So first example, we just have used basic gates. We used NOT gate, AND gate and OR gate. Here you can see we have used AND gate and NOR gate. So you can simplify any expression or you can design any circuit diagram using different gates. So what all we have learned from this chapter? We have learned what do you mean by gate, and what are the different types of gate, and how can you design a circuit diagram using gate. The weightage given for this chapter for second PUC computer science is 4 marks. 1 mark question, you can expect some definitions or what do you mean by logic gate or any truth table for different gates or symbols for different gates, and you can expect 1 3-mark question where you are going to explain different gates with truth table, definition and symbol, or you can explain designing the circuit diagram for using just basic gates and using basic gates and derived gates. With that, I am going to end today's session. Hope you all understood this session. Meet you in next session. Thank you.